Before we jump into the computer, let us make sure we can really read contours. We looked at a simple example in the previous section, so let us study some more patterns we can expect to come across or have the need to create. So what I'm going to talk about is visualizing landforms and interpolating surfaces. So the very first thing we're going to do is just simply look at some patterns here. So let's take a look at this example here, drawn on engineering paper, so you can replicate this on engineering paper if you would like to. And we notice that we have some contours here. So this is in plan view. So let's kind of observe what we see here. So first thing you need to know is that we're looking at this in plan view. There is a section line running across here, but for now we're going to ignore that section line. The next thing we notice that this is at 1 foot contour. So we have 1250, 1249, 1248, 47, 46, 45, so on and so forth. We also notice that this is a plan contour drawing of existing conditions because the lines are dashed. So you can see our contour lines are dashed here. We notice that the leftmost contour, which is labeled 1250, is our high point, and on the very right side we have elevation 1245, so this is our low point. We also notice that our contours are evenly spaced out, so that means that we don't have an area where there's super steep slope and then it gets flat sort of thing. It's pretty consistent slope here. We don't know the linear length, so we don't know how long it is from 1250 to 1245. We don't know what that length is. The only thing we know is that things are kind of evenly spaced out so far. So since we have a little section line here, this means we're probably going to take a section, and we are. So we're just looking at where this line cuts across these contours and what that might look like in section view. So over here we have 1250. So now we're taking a look at our section and going to take some observations of this. So again, this is in section view, so we're just cutting along this line and taking a look at what that slice looks like. So this is at 1 foot contour as well. We notice here on the left side we have 1250, 49, 48, 47, 46, and 45. We also notice that the line, just as we suspected, is a straight line. It's not parabolic up or down or anything weird like that. It's just a normal straight line running across here. And we still don't know really what the horizontal distance is, and we can make some assumptions just based on what this slope looks like here. So another question you might have is, how do you create this section? So oftentimes you'll look at some contours and maybe it's not very straightforward what's going on there, and it can be helpful to be able to take a section. So how do you take a section? Well, the first thing that I usually do is draw a line in plan view where I want to take that section. So in this example here, I want to take it across kind of perpendicular to all of these contours. The next thing I do is where the contours are touching my section line, I just draw a line all the way down. I don't know exactly how far down I need to go, and to determine that I'm going to take a look at, so for example this first one, the contour 1050 is touching my section line, so this line comes all the way down and I look for 1050 and I see it's there. And I do the same thing for 1249, I see it's here, for 1248, 47, 46, etc. And what you're going to end up having is a series of points, and then you're going to connect these points together to create your section cut here. So this is how I know what this line looks like. So let us take a look at another example now. What if our contour lines are not evenly spaced out? Maybe they get really squished together here in the beginning, and then they're a little bit more further spaced out as we go out. What would that look like? So again, this is another plan view that we're looking at. We notice it's again a 1 foot contour interval. We notice that the leftmost is our high point and the rightmost is our low point. One thing that's different from this one compared to the previous one is that our contours are not evenly spaced out. The contour lines are very close together here on the left side of our plan view here. And then we're going to use our section line again to take a cut. So as I mentioned earlier, the left side is our high point, the right side is low, so water is going to be flowing from the left to the right. Let's take a look at our section. So compared to before, this is pretty much the same as it was before, 1 foot contour interval. We don't have a straight line. We kind of have a parabolic type line. Kind of bends inwards, kind of like a half of a U shape. Let's take a look at another example. What happens if it does something like this? So all the lines are really squished together on the right side and a little bit more spaced apart on the left side. What is this going to look like? So again, we're taking a look at plan view. Same as before, except the configurations are a little bit different. Our high point's to the left, low point to the right, water's flowing from the left to the right. All of our contours are squished together to the right. So let's take a look at our section. And this is what our section reveals. So this is something that it's kind of like an upside down U. So we still have the same type of water flow. It's kind of a sheet flow that's going across here. So this is again 1 foot contour interval, and it somewhat looks like a mound from sideways view. Let's take a look at another example, a little bit more interesting. So now in this example, this is another plan view. We have both existing and proposed contours. And I know that because remember, our proposed contours are this thicker, bolder line. So again, this is a 1 foot contour interval, and the very far left is our high point, to the far right is our low, so we know water is flowing from the left to the right. And it looks like there's quite a significant amount of space between proposed contour 1246 and proposed contour 1247. So this is going to suggest that there's probably most likely going to be a flat area in between here. So we're trying to propose something flat. Also notice the direction of our proposed contours. Some of them are kind of going up the slope, and some of them are going down the slope. So this one's going into our hillside, where this one is coming out of our hillside. So what is that going to look like in section view? It's going to look something somewhat similar to this. So again, we're looking in section view, the same 1 foot contour interval. We notice that around elevation 1247 we have created a flat area. And notice that part of our flat area cuts into the hill, and part of it is filling the hillside. So over here on this side. So cut means to carve out earth, and fill means to fill in the earth. So we have both situations going on here. And just going back to this diagram here, as a landscape architect, you definitely want to try to balance your cut and fill as much as you possibly can. And the reason why is because if you have to bring in excess fill or haul away excess cut, it can be very costly to your client. So we do really strive when we're grading to try to balance the cut and fill type situations. There are other environmental impacts associated with hauling away or bringing in earth. For example, if developing in an area that normally floods and one brings in excess earth, then what was there normally, it can raise the flood line in that area or neighboring areas. This principle is very similar to filling a bathtub up to the rim with water and then stepping into the bath. As your body or the earth displaces the water, it will rise up and overflow the bathtub or raise the flood line in that area. So you can cause kind of neighboring areas that weren't originally in a flood zone to flood. So in some cases, this may be unavoidable. Maybe you're intentionally needing to fill it in, and maybe you are wanting a certain area to flood. Maybe that's the desired effect that you're going after. But if it's not, this is something that you definitely want to take under consideration. So I do have some more examples in the written text version of this. So if you want to take a look at maybe a drainage ditch or a berm, how to create a berm, how to grade one in, you can definitely take a look at the written documentation. The next thing I want to talk a little bit about are the contour rules. So there's a lot of things that you can do with contours, but generally we have some kind of rules that we try to follow as we are doing grading. So the first one is going to be all points along a contour line must have the same elevation. So this is kind of the definition of what a contour is. So we have a series of points, and as we connect each of these points, it creates a contour line. And each of these points must have the same elevation in order for it to be classified as a contour. If they don't have the same elevation, they're not coplanar. It means it's a 3D line and it cannot be classified as a contour. So if you have one on the end here that's 101 and everything else is 100, then that doesn't count. It's not a contour line. The second one, the second rule, is contours closing on itself within the limits of a map is either a summit or a depression. So it could be a summit or a depression, and again, to be able to figure out which it is it a hill or a bowl shape, is to take a look at what the elevation values are for those contour lines. Contour lines do not cross. So for the purposes of what we do, we don't create cave-like or tunnel-like spaces. So if you have contours that are going underneath another contour, you're kind of creating a cave or a tunnel-like space. And when we do that, we end up creating a divide by zero type situation, which we want to avoid. So there may be certain cases, instances as you're grading that you want to create that vertical drop, such as a retaining wall. So again, in the computer, we want to create that vertical drop. We're going to move the contours really close to each other, as if it appears that the contours are stacking, but they're not really stacking. You're going to have still a very small amount of space between those contours, such that you don't create the divide by zero problem. So again, contours do not cross. Number 4, contours close together indicate a steep slope. So remember, in our previous example, we took a look at this. So if the contours are really close together, that means that area is going to be really steep. Contours spaced far apart indicate a flat area with very slight grade. So again, in our example, that would be the stuff on the right side where the contours are very far apart. The steepest area will be perpendicular to contour. So if you have a series of existing contours like we do in our example here, and then we have a stack of proposed that are really close together, that's going to be pretty steep there. So it's kind of like a retaining wall, and we'll see some examples of that. And finally, in case you didn't already know, water flows perpendicular to contours.